In an earlier session, we began our discussion on the topics of vectors and vector calculus. In particular, we defined the so-called linear vector space, whose elements are known as the vectors. In today's session, we're going to talk about the concept of linear independence. A finite set of vectors, say v1, v2, vn, are called linearly independent if c1 times v1 plus c2 times v2 plus ... plus cn times vn equal to phi, where phi is the null vector, implies that c1, c2 and cn are all 0. In other words, if we demand this condition, then only possible solution for this equation must be such that the all coefficient numbers c1, c2 and cn are 0. Let us consider an example as you see it here. Show that v1 which is equal to x and v2 which is equal to 8 times x are linearly dependent. So in order to check whether v1 and v2 are linearly dependent, we need to check whether if I demand that c1 times v1 plus c2 times v2 equal to phi, which is 0 here, the null vector is 0 for this case, implies c1 equal to 0 and c2 equal to 0 or not. So if you denote the equation 1, which is c1 v1 plus c2 v2 equal to phi, if you demand the equation 1 holds for all values of x, then at x equal to 1, the equation 1 implies c1 plus 8c2 equal to 0, and at x equal to 2, the equation 1 implies 2c1 plus 16 times c2 equal to 0. Now you can check that equation 2 or 3 only implies c1 equal to minus of 8c2, which is not 0 in general. It could be 0, but it need not be 0. Still, one can satisfy the equation 2, 3 for c and c1 and c2 not being 0. Therefore, v1 or v2 are not linearly independent. In other words, if you impose the condition c1 times v1 plus c2 times v2 equal to phi, it does not necessarily mean the coefficients c1 and c2 are 0. Hence, the vector v1 and v2 are not linearly independent, or they are linearly dependent. So that u equal to x and v equal to x square are linearly independent. Again, we consider the condition c1 times u plus c2 times v to be null vector, which is 0 here, or c1 times x plus c2 times x square equal to 0. Since this condition to be satisfied for all x, then at x equal to 1, it implies c1 plus c2 equal to 0. At x equal to 2, it implies 2c1 plus 4c2 equal to 0. Now, if you solve the equation using equations 1 and 2, as you see it here, it implies the c1 equal to 0 as well as c2 equal to 0. In other words, c1 times x plus c2 times x square equal to 0 for all x necessarily implies that c1 equal to 0 and c2 equal to 0. Therefore, the vector x and x square are linearly independent. Let us now consider another example. Show that f of x equal to sin x and g of x equal to cosine x are linearly independent. Now we can use the definition of linear independence, that is, if you require the combination a times sin x plus b times cosine x equal to phi, which is 0 here, for all x, then at x equal to 0, it directly implies b equal to 0. At x equal to pi by 2, it has to be a equal to 0. Otherwise, this condition cannot be satisfied. Clearly, as you see it here, the sin x and cosine x are linearly independent. Let us now introduce the concept of basis vectors. If every vector of a linear vector space capital V is expressible as a linear combination of a set of linearly independent vectors, say v1, v2 and vn, then these vectors are said to span the vector space. These vectors are known as the basis vectors. So now let us introduce the general notation to represent the basis vector. So let us consider the vector A, which I often write as ax times I cap plus ay times j cap plus ak times k cap. Now let us introduce the notation for the basis vector as e1 cap, which is the same as I cap, which is the same as ex cap. Similarly, e2 cap, which is same as ey cap, which is equal to j cap, and e3 cap, which is the same as ez cap, is equal to k cap. And let us now denote ax component of the vector to be a1 and ay component to be a2 and az component to be a3. Then we can express the vector as a1 times e1 cap plus a2 times e2 cap plus a3 times e3 cap. Or we can write the vector A as a summation over I to n ai times ei cap. So as you see it here, if the set eai cap can be said to be a set of basis vector, then any arbitrary vector, say b vector, can be expressed as bi times ei cap summation over I equal to 1 to n. Here the term bi is called the ith component of the vector b, and the capital N is called the dimension of the linear vector space B. So in a three-dimensional vector space, we can have three linearly independent vectors. I hope you have enjoyed today's session. In case you have a question, comments, or a suggestion, please feel free to write them below in the comment section. And if you would like to follow the physics discussion here, then you are welcome to subscribe to this channel.